Hello everyone, welcome to lecture 51 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on realizing electromagnetic cloaking using metamaterials. Here is the lecture outline. We will have a brief introduction to the topic and then we will go into the cloaking theory based on metamaterials or metasurfaces in this case. We will also take up some examples of metamaterial based cloaking. We will discuss metamaterial mirror based cloaking, split ring resonator based cloaking, and then we will take up near pie shaped structure cloaking, where we will be discussing rectangular cloaks, an eye shaped cloak and a triangular shaped cloak. So, from the beginning of this course we have been discussing this particular feature of metamaterials, that these are artificial materials with some properties which are not found in nature. So, that allows you to make some unique properties that enables wide range of applications in engineering, of which one key application is always invisibility cloaking. That means you can make an object invisible to the human eye, and this can be achieved by metamaterials by means of manipulating or bending light in unnatural ways. So, if you can precisely engineer the structures that can allow light to bend around any particular object, you can make those objects disappear. So, that is where the field of metamaterial cloaking shows the promise, because you can use metamaterial cloaks that can, as you can see here, that can bend the electromagnetic waves around. Okay, so this is the object that is being hidden from the electromagnetic waves because of this structure that is basically made of metamaterials that can bend the electromagnetic rays around this object, and then after they exit from here, they exit in such a way as if there is nothing present in this particular ring. So, this kind of things can be achieved by manipulating the refractive index of the metamaterials, right. Now, what we understood from our previous lectures is that a major challenge in this field is basically achieving broadband invisibility. So, it is difficult to make objects invisible over a wide frequency range, and that too for all the viewing angles, right. So, people have explored different methodologies such as use of plasmonic materials, integration of metamaterials with some spatially varying structures, and also investigated non-resonant metamaterials which are broadband in nature. So, this kind of developments have basically allowed more efficient and versatile cloaking across broader frequency range, typically from microwave radiation to visible frequency range. Now, what are the potential application of this kind of broadband invisibility? The first thing comes to your mind should be defense, where you can conceal military assets such as aircraft from radars. So, that is basically the stealth technology people are talking about. Then you can have telecommunications, where you can use this kind of technology to enhance the signal control and also improve the communication systems. They can be also used in medicine by enabling more effective imaging techniques using light or any other electromagnetic waves that can actually help you in better diagnosis, okay, and targeted treatment. Now, with this introduction, now let us look into the cloaking theory based on metamaterials. Okay, in the previous lectures, if you have seen, we have discussed everything in terms of transformation optics, but here we are mainly focusing on metamaterials or their 2D counterparts, metasurfaces, right. So, metamaterials are extensively used in ultra thin carpet cloaks, which we have discussed earlier, due to their precise control over phase and amplitude, right. So, metamaterials are basically periodic structures of unit cells, and that allows local phase compensation if you vary the unit cell size. So, some sort of development, okay, in the transmissive metamaterial based cloak can be seen here. Okay. So, in this figure you can see that there are basically 3 layer frame structure which are based on very thin metamaterials, or you can call them as 2D metasurfaces. So, this layer 1, 2 and 3 are basically the 3 transparent metasurfaces with their respective phase gradient. So, you can see that the unit cell sizes are not same throughout, they are basically changing. And this is the direction of the electric field and the magnetic field and the wave vector. So, what we are considering here is that the electric field is along the y vector. So, you can say it is basically a y polarized plane wave that is normally incidenting, right. Now, what is the purpose here? You are basically making a cloaked region. Okay. So, this is a boundary made of PEC. Okay. So, inside this whatever you keep, okay, that will not be seen by this incoming light. So, at the end of this you will see that the wave basically emerges undisturbed as a plane wave that demonstrates the effective cloaking property. So, here in the schematic you can also see that how things work. So, this is the incident beam and this is the first layer, and you have phase gradient this way. Then you have the second layer, this one, and this is the cloaked region. So, these are basically the angles, okay, alpha, and then this is the refraction angle basically from this or the transmitted angle from this metasurface, and then you have another metasurface over here which basically bends it down this way, and then again it transmits as if nothing has happened in between, and you just have the parallel rays coming out, right. So, all those things are possible because now you are able to control the refraction using metasurfaces. So, you are not only dependent on the Snell's law, you are basically using a generalized Snell's law of refraction. So, it can be written as sin theta t minus sin theta I will be equal to lambda naught by 2 pi dou phi by dou x. So, theta I is basically the incident angle, theta t is the refraction angle. Okay. So, here you can see that its normal incidence. So, theta I is basically 0, theta t is basically alpha, and lambda naught is the working wavelength, and you can see there is an important term here, that is d phi by dx, that is basically the phase gradient. Okay. So, x is this particular axis. So, from this equation you can understand that the refraction angle theta t can be fully controlled by adjusting the transmitted phase gradient. Now, you have got that extra control, that is what the metasurfaces or the 2D metamaterials are bringing into the picture, right. So, this concept basically enables the design of transmissive invisibility cloak using metasurfaces. So, the design principle, as I have already mentioned, that you can see here that it bends like this, again it goes back in the opposite direction, and finally it escapes in as a parallel beam. Okay. So, to begin with, you are considering Y polarized light to be normally incident on this metasurface 1, and on the left and right side of the structure you can see you should have opposite phase gradient, so that this beam bends this way and this beam basically bends in the opposite way, means in this particular way, right. So, on the left side of the metasurface 1 you are basically bending it like this, right. So, the angle of refraction is basically related to the phase gradient, and you can get it like sine of minus alpha. So, you can consider this angle as minus alpha minus sin theta naught, that is basically theta naught the incident angle, equals minus lambda naught by 2 pi d phi 1 by dx, and on the right side you have sin alpha, this one, minus sin theta naught will be equal to lambda naught by 2 pi d phi 1 by dx, or you can also say d phi 2 by dx. Okay. So it all depends on, so because we are considering meta surface 1, we can consider this phase gradient as d phi 1 dx. Similarly, the left and right side of the meta surfaces 2 and 3 will also be denoted like this. So here the incident angle is also alpha, the transmitted angle is also alpha, so you have, or minus alpha rather. So you have this term, okay, and you have this term on the right, okay, that is sin alpha minus sin minus alpha equals minus lambda naught by 2 pi d phi 2 by dx, and then you have on this side you have sin minus alpha minus sin alpha equals lambda naught by 2 pi d phi 2 by dx. In this case, this is the incident angle and theta naught will be your transmitted angle. So you can write sin theta naught minus sin alpha will be equal to minus lambda naught by 2 pi d phi 3 by dx, and on this side you can write sin theta naught minus sin minus alpha will be equal to lambda naught by 2 pi d phi 3 by dx, right. So here as you can see that alpha is basically the value of each corresponding angles. Now if you consider the case of a normal incident light as shown here, you can simply take theta equals 0 degree, right, and these three terms d phi 1 by dx, d phi 2 by dx and d phi 3 by dx, they basically represent the phase gradients of meta surface 1, 2 and 3, right. So using this you can always do beam splitting, beam steering and beam collection, right. All this, because you have the control on the phase, you can basically bend the transmitted beam in whichever direction you want, and you can actually do that for all these different applications, right. So these effects basically allow a plane wave to bypass obstacle, okay, and that finally allows you to restore the wavefront, and this is effectively giving you a cloaking effect because you are bypassing one particular region in the path. So with this concept, now let us go into some practical examples of metamaterial based cloaking. So let us first consider metamaterials mirror based cloaking. So let us consider this particular unit cell for the metamaterial mirrors, okay. So it is basically built with a 2-layer square copper metal structure, so one on the top, one at the bottom, okay, and then there is a dielectric layer of polyimide in between, which has got a relative permittivity of 3.5. Now what are the dimensions being used here? The thickness of the metal on the top and the bottom layer is taken as 0.2 micron. The thickness of the polyimide layer is 30 micron, and the P, that is the periodicity of the unit cell, is 138 micron, okay. Now as you can see that this very A and B are basically the length and the width of the metal layer, okay, and that is basically adjustable. So this particular table shows different structure size where you are basically changing A and B, okay, and you can see that when A equals 100 and B equals 107, the phase is 0 and your reflection amplitude is 0.9344, right. So as you keep on changing this dimension, you can gradually increase the phase, keeping the amplitude of the reflection almost similar. Now what is the purpose of this bottom metal plate? Because it is more or less always same, the purpose is to enhance the reflection, right. So based on that, now let us make a mirror based cloaking. So what you are doing here is that you are showing the schematic of the cloak first, okay. So you have these 4 mirrors present, 1, 2, 3 and 4, okay. So this mirror based cloaking is also a type of metamaterial cloaking approach, where you can see that you are basically using curved mirrors to redirect waves around the cloaked object that will be kept here, okay. So the design of a transmissive invisibility cloak using metamaterial mirror is shown in this figure. So what is seen clearly that there are 4 mirrors labeled as 1, 2, 3, 4, and then there are 2 vertical mirrors also present on the both sides of this rhombus frame, Okay, and this particular design basically uses the generalized Snell's law for the reflected wave control that we have seen earlier, that we have basically seen for the transmitted one. Similarly, you can also have for the reflection generalized Snell's law. Okay, and there also you will see that the reflective angle or the reflection angle basically can be controlled only by the phase gradient variation. So this is how the schematic is showing that the principle of cloaking, how it is working. So you can consider plane wave incident on this metamaterial mirror. Okay, then it is getting reflected at an angle B, which is again further reflected. Okay, so there are phase gradient along this and this. Finally, your objective is whatever is the incoming wave, after crossing that region you should also get the same kind of parallel incoming wave, okay, or outgoing wave. So that plane wave should not change in direction, so that will allow you to have this cloaked region. Okay, so what are the key design principles in this case? You have to remember that you are using all metal mirror configurations. Now, if you consider all metal mirror, that will also work in this case, but typically they are limited by the Snell's law, right, where your incident angle will be equal to the reflection angle. So that will basically restrict your flexibility and it will require a fixed cloaked region. But if you make this with meta surfaces or metamaterials to work as mirrors, that will give you much greater degree of freedom, because it allows control of the reflection angle from the gradual phase distribution, and in that case the incident and the reflected angles may vary. So after covering the obstacle that you are going to cloak with this kind of metamaterial based mirror cloaks, okay, you will see that the electromagnetic wave that is outgoing appears to be restored as if it is passing through the obstacle undisturbed, right. So how this cloak is going to be effective? This is mainly because of the metamaterial mirrors. They are able to precisely adjust the reflection angle, okay, and bring the outgoing wave back here, okay, in the same path as the incoming wave. So this mechanism successfully produces the cloaking effect by preserving the wave front, right. That is the most important thing. Now let us look into another example, which is based on split ring resonator that is used for cloaking. So split ring resonators are well known now structures. These are sub-wavelength structures with some ring gap. As you can see, this is a copper one on Rogers dielectric. Okay, this can be used in metamaterials for cloaking. So it has been seen that split ring resonators exhibit very strong resonances at specific frequencies, and they can also produce negative refractive index. Okay. Now, if you arrange split ring resonators into patterns, that allows creation of cloaking metamaterials. Okay. So here is the front view and the back view of the proposed unit cell. So you see at the back you just have a copper patch, on the top you have this split ring resonator printed, right, that is on the Rogers dielectric, right. So you can basically make an electromagnetic cloak using serially interconnected split ring resonators. So the split ring resonators shown here, this is the unit cell. They can be connected via transmission line and wrapped around a cylindrical object, as you can see in this particular figure. So here specifically there are 7 unit cells of split ring resonators which are connected to each other to cover this cylindrical cloaked structure. And how it works, that electromagnetic waves are now guided around this object via the split ring resonators, and the waves are received on the opposite side, okay, effectively cloaking the object. Next we move on to another type of structure, that is a pie shaped structure based on the geometry, okay, that can be used for cloaking based on near zero refractive index metamaterial. So this is the structure I was talking about. It's a near pie shaped structure which is basically made of two orthogonal copper arms that form a pie kind of a shape. Okay, and the design parameter for this kind of structure is listed here. So you have all these parameters D, E, F, G, H, I, H, L, M, N, okay, P, Q, S, all these things are given in terms of millimeter, right. Now the series branch that you see for this unit cell structure must basically contain an inductance or capacitance, and the corresponding shunt branch must contain the opposite order of reactance, right, and that you can see from the equivalent circuit of the unit cell, right. There are two unequal gaps also present, okay, at each arms, and this gives you a capacitive effect which is denoted by G and S. Okay, so these are the two gaps. You can see they are in different, the gaps are different, and conversely you will see that each unequal metal arm is also responsible for generating inductances, right. And the overall structure has got all the copper lines to have the same thickness of 0.035 millimeter, and this particular structure is constructed on epoxy resin fiber FFO substrate material which has got dielectric permittivity of 4.2 and dielectric loss tangent of 0.002, right. So this is the rectangular electromagnetic cloak that is designed unit using this kind of pie shaped unit cell. So this is the cloak. So anything you keep in the center of this cloak is hidden. Okay, so this is the top view, okay, that you can see. So you can call it as core shell kind of a structure. So the four walls are basically having dimensions of 20 by 20 millimeter square, each with FR4 substrate material, as you can see from the figure. So in each wall you can also see that 2 by 2 unit cell are basically used, where each unit cell is basically having a pie shaped structure. Now what we are clocking here, we are clocking an aluminum cylinder that is placed centrally, okay, and we maintain the distance from the cylinder center to the cloak walls on both sides to be 10 mm. Okay, and in this particular case they considered the height of the cylinder to be 20 mm, the inner radius is 3 mm and the outer radius is 4 mm. Okay, so it is not a solid cylinder, it is also a core shell kind of cylinder, right. So in this particular design, the cloaking operation is based on scattering cancellation method, where the dielectric shell basically cancels out the scattering from the core, and the electromagnetic wave in this case continues to move along the original path, that's restoring the wavefront and giving you the cloaking effect. Next we look into another type. So instead of having rectangular cloak, you can also make I-shaped cloak using the same material. Okay, so this is the schematic of, or you can say the top view of the I-shaped cloak with the metal cylinder in between. Okay, so the structural details here, okay, remains very similar to what we have seen in the previous slide. So it utilizes the same number and the size of the side walls as it was there in the rectangular cloak region. Okay, so as you can see, the four walls basically arranged to form an I shape in the figure. The pair of walls, they are basically joined at one end, and typically the angle is around 45 degree. And this is the result of the electric field distribution and magnetic field distribution along this xy plane for the object, considered at clock frequency of 5 gigahertz in this case. So you can see that the electric field outside is pretty homogeneous. So that is how you can say that the effective cloaking is taking place. Okay, so overall scattering width is only 0.12, right. So it is giving you very little scattering signature. You can also make a triangular shaped cloak using the same kind of material. So, in this case, instead of 4 walls, it will be 3 walls, that is forming a triangular cloak shell. So, all the walls are considered to be of equal size, that is consistent with the previous designs that we have discussed. Here you will see that the two walls basically meet at 45-degree angle, and then you place the third wall behind them to complete the triangle. And here also you can study the electric field and the magnetic field distribution along the xy plane or in this particular plane, okay. And you can see that you can achieve successful cloaking between 5 gigahertz and 6.5 gigahertz. So, this is the result that has been plotted for 5.67 gigahertz. So, you see the surrounding medium more or less everywhere the electric field remains constant, okay. There is no separate scattering signature which is revealed of this particular object, okay. So, that way you are able to get a triangular shaped cloak using metamaterials. And here you can further lower the scattering width. So, it comes out to be 0.024 at 5.67 gigahertz. So, that is demonstrating the best performance of this cloak. So, with that we come to a conclusion of this lecture. So, we will start discussing about the transformation electromagnetics for antenna applications and some metamaterials for stealth technology in the next lectures. So, if you have got any query regarding this particular topic, you can always drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.